Hello and welcome to Mostly Weather. I'm Jeff Norwood-Brown, and in this episode we'll be discussing atmospheric oscillations, also known as global drivers. Joining me today are Mostly Weather regulars, archive aficionado Catherine Ross, socio-meteorologist Helen Roberts, and severe weather advisor Penny Tranter. Our very special guest today is Adam Scaife. Hello, Adam.
Hello, Jeff.
Would you like to tell us a little bit about your work here in the Met Office?
My official job title is Head of Monthly to Decadal Prediction. That's a bit of a mouthful. What that really means is Head of Long Range Forecasting. We make predictions that bridge between weather forecasts that everyone's familiar with and climate projections that are used to advise government and so on about climate change. It's the bit in the middle that we do everything from 1 month ahead to a season ahead, out to a few years ahead.
Right, okay. So in this episode, we're going to be talking about atmospheric oscillations, and you're our expert, Adam. What are they? What are we talking about here?
This is a broad topic. There are actually very few examples of true oscillations which have a kind of restoring force that make them swing one way and the other, a bit like waves on the ocean, if you like, where gravity pulls it back down as the wave rises. So there are very few examples of true oscillations. There are some, and we can talk about them. There's something called the quasi-biennial oscillation, which is perhaps the most spectacular example. But many of the other things that we call oscillations are really fluctuations with a broad spectrum of timescales, so they can fluctuate month to month or year to year. Nonetheless, although they're somewhat irregular, they're crucially important for regional weather and climate.
So is there any example of one of these pseudo oscillations, if you like, that our listeners may be familiar with?
The one that's perhaps most relevant to people in Europe and the UK is the North Atlantic Oscillation. So the North Atlantic Oscillation is this variation in the pressure gradient between the region near Iceland and the region near the Azores. Now, when that pressure gradient is very steep, so there's a sharp decline of pressure as you go towards the pole and to Iceland, then the physics of the atmosphere means that the winds will be very strong because the pressure, the temperature, and the winds are all in balance in the atmosphere. And that's the main reason why, for example, in some winters we have very strong westerly winds with lots of storms, lots of rainfall, a mild winter. And then in other winters, the pressure gradient slackens, the winds drop off, and then we get cold, dry, extreme, and sometimes snow in winter. So that's kind of a nice local example.
I've heard of El Nino. Is that one of these oscillations?
Yeah, that's right. I mean, in terms of the global picture and global climate, the El Nino Southern Oscillation, this is a coupling between ocean fluctuations and atmosphere fluctuations, is perhaps the most important. It certainly has the most widespread impacts across the globe. If you look year to year, it is the single biggest factor that governs year-to-year changes in the tropics. And there are also some extratropical impacts, even for Europe and the UK.
The frequency of these, are they all the same? Or I think you've hinted that they are all different, are they? Some are more regular than others?
I guess if you were to put them on a spectrum of how regular they are, then the least regular are things like the North Atlantic Oscillation. There isn't really a preferred period there, even though, of course, people have looked for that using historical data. And then as we come through, you get things like the El Nino, which does have some regularity. It tends to have a preferred period of a few years. 2 to 5 years typically, but there is a peak there. There is a kind of regular cycling, if you like, to some degree. And then you get to the very regular things, which are much rarer, like the quasi-biennial oscillation, which is about 28 months in period. I know that sounds like a weird number, 28 months. Why on earth should it be 28 months? And there was a big mystery about that historically, but now that's been resolved. It's not related to the annual cycle or anything, so it's not 24. It is actually slightly different, 28, but that is much more regular. And there is a fluctuation in that period, but it tends to hover around 28 months.
It sounds really, really interesting. How do these oscillations come about, and are they linked to any other global weather patterns like jet streams, for example?
That's a great question. It's a subject very close to my heart, and we spend, 30 odd years or whatever studying these mechanisms. Of course, we haven't got to the bottom of all of them, but some of them are very well understood now, and they are rather different. So it depends which of the features that we're talking about. I mean, one of the things, going right back to when I started in this field, one of the things that struck me about meteorology is that if you look at it from a physics point of view, then it's really about fluids and fluid dynamics. The atmosphere is a fluid. There aren't solutions to those problems. They have an infinite number of possible solutions. It's not like a maths problem where you can solve it and then it's done. The atmosphere is chaotic. There are all these different scales and interactions, and the things that we're talking about now have very varied mechanisms. And I think that's what makes the whole topic really interesting. If we take the El Nino, for example, then one of the simplest models of that is that heat builds up in the West Pacific. It builds up and then eventually it discharges and produces an El Nino. And then there is a kind of feedback mechanism involving ocean waves propagating across the Pacific basin that trigger the whole thing again. And it's these time scales of propagation of waves across the basin and the discharge that set the periodicity of the phenomenon. If we look at other things like the quasi-biennial oscillation, that is, I mean, perhaps the most spectacular thing in the atmosphere, the most regular thing in the atmosphere after the cycling of the seasons. We all know that winter is followed by spring, and we can rely on that, is very regular. Lots of these other things are much more irregular, but the quasi-biennial oscillation really is a series of oscillating stripes, if you were to plot it out on a graph. The mechanism for that is rather amazing, really, because it comes from very small scale fluctuations in the atmosphere. Every time there's a thunderstorm in the tropics or a region of rainfall and convection, this triggers so-called gravity waves. These are waves like buoyancy waves in the atmosphere. And these are very small. They're only on a scale of 10 kilometers and take an hour or so to go up through the atmosphere. But their cumulative effect in the upper layers of the atmosphere drive this global change in the winds, so all the way around the tropics. The mechanism, I'm not going to go into all the details, but the mechanism which we now understand allows for a flipping and a selection of different sets of waves. So when the quasi-biennial oscillation is in one phase, it'll select gravity waves that are propagating eastwards, and they will help to strengthen it. And then when the oscillation flips, it'll select these other waves, and the waves help to drive and force the oscillation. But the whole thing emerges out of chaos. So you're starting with a lot of little waves, all random, and the thing that emerges is this beautiful global scale jet stream, perfectly zonally symmetric, propagating slowly down through the atmosphere and then flipping into the next phase and slowly down.
Adam, I think you've sort of touched on this a little bit already, but I'm just wondering how these oscillations and global drivers interact with each other. Presumably they do to some extent. Can they sometimes both work in the same direction and perhaps other times they're sort of fighting against one another?
Yeah, that's a good question, isn't it? If you look at extreme weather, so for example, I'm sure we all remember the winter of 2009-10. In that winter, we had the most negative North Atlantic oscillation in the historical record. And the pressure gradient, I think, was something like 20 or 30 millibars below normal. So it really was a winter where there was no jet stream, if you like. It was wiped out. So we had very still winter, very cold winter. And some of the drivers, when you look at them and ask which way are they pointing? So, for example, which way was the North Atlantic oscillation pointing? Well, it was very strongly negative. But some of the other things that affect the North Atlantic oscillation that actually help drive a change in the North Atlantic oscillation, because as you say, they do interact, were also pointing towards the same direction. So, for example, we had an El Nino in that winter. We now know that El Nino increases the chance or helps to drive a negative NAO. And we had an easterly QBO in that winter. And we know also, both from historical records and computer experiments, that easterly QBO helps to drive a negative NAO. So all of these drivers in that winter were kind of pointing in the same direction. And that's one of the reasons that we had such an extreme winter. So although these things sound a little bit academic, esoteric, and a little bit remote, actually they are really important in determining societally important events like that winter of 2009-10.
I was just wondering, Adam, and obviously you've listed off a few oscillations and there are a few others, but are we still finding them? Do you think we've got to the end of the list yet, or are there still some more out there? El Nino was first sort of identified in the 20s and going since then, but have we got there yet?
I think we've found all the big ones, all the obvious ones. We've got a century or so of decent meteorological observations. Some of these things were discovered in the 19th century. So Gilbert Walker, for example, did lots of early work with really amazing pioneering work using very early and very limited records of weather observations in the tropics, and pointed out the southern oscillation and the North Atlantic oscillation, actually using early pressure records. So those things are the two big ones, I guess, one in the tropics, one in the extratropics. And then since then, we've added on lots of other things. So that the quasi-biennial oscillation was not discovered until about 1960 or late 1950s. In fact, that was discovered by Met Office scientists. So some of them have been discovered in more recent times. And then I guess in the last few decades, we've found some things on decadal timescales that were not really emphasized or known about before. So it turns out in the Pacific, there is strong decadal variability. There's still an argument amongst the academics whether this is just a kind of residual summation of the El Niños and La Niñas that are going on, or whether there really is a decadal thing there that's actually fluctuating from one 10, 20-year period to the next 10, 20-year period. I mean, that's only really the last couple of decades, I think, that's really been talked about a lot. But I think we found all the big ones. There are a few other things that are not so well recognised that I think require more research, though.
Thanks, Adam. I mean, it's really, really interesting to hear about the history and discovery of all these different oscillations. I just wanted to ask two questions, really. Can we forecast what they're going to do? And if so, how far ahead? And also, do we understand the impacts that result from these oscillations in terms of weather patterns, whether they're severe or whether they're business as usual or benign?
Those are great questions, Penny. I mean, they are the core questions to lots of research programs in our group and worldwide. In terms of predictability, we obviously have our current forecast systems at the moment, so I can tell you how good they are. These are all probably underestimates, of course, because our forecast systems are far from perfect. We still have errors and approximations even in the best computer models. But we already know, for example, that El Nino is very highly predictable a season or two ahead. There is predictability even out to a year ahead and a little bit further. So, for example, if we start now, we can predict maybe not only the coming winter, but sometimes the winter after as well. So more than a year of predictability for El Nino and La Nina, especially when there's a big oscillation coming, a big event.
Can we also predict how the different oscillations interact with each other as well?
I think the interactions are a little bit difficult. When Helen asked a similar question, I sort of slightly sidestepped it by saying that there are times when the effects of the different oscillations add up. And that's obviously a superposition, just adding them up, summing them, rather than interaction. And so I think we know a little bit less about the interaction than we do about the kind of linear summation, just adding these things up. Your other question, though, about the regional effects is also really important. I mean, that's where it really starts to become worthwhile to investigate these things, right? Because what we see, particularly in long-range forecasts, is good predictability for things like El Nino, but then we have to go that extra step and say, what is that doing, say, to the regional climate in South Africa or India or Europe, indeed, or wherever? And we can do that using the computer models. So they often produce, for example, if we run a long-range forecast and there's an El Nino coming, and then we look at what the forecast is showing us globally, we can see patterns in the rainfall and temperature that look very similar to El Nino impacts in past historical data that we've seen globally. So we can verify that the forecast is making sense. If you can do that, gives you a lot of faith in the forecast, right? Not only do we have an independent computer model based on physics telling us this, but we also know that it's got an El Nino in it. And we also know from historical observations that that's what El Nino does. If you put all that together, it gives you a lot of confidence and allows you to make a forecast of the regional climate, even way beyond these weather forecasting timescales.
So as I understand it, Adam, we're currently in what's being referred to as a triple dip La Nina. So can
Yeah, that's
you
right.
explain what we mean by that and perhaps some of the impacts that that might have globally?
So by triple dip La Nina, we mean that we're now in the middle of a third La Nina on the trot. We should emphasize that La Nina and El Nino occur around Christmas time, hence the name. It's a Spanish word, comes from South America, which is obviously very close to the center of action of El Nino and La Nina. So the whole thing is phase locked, as we would say, to the winter period. And what we've seen is the last 2 winters had La Nina. The coming winter has La Nina, hence the phrase triple dip, even though it slackens off in the summer period when it's not maximum strength. So we've had 3 on the trot. Whether there is any real physical mechanism that encourages another La Nina just because you've had 1 or 2 in the previous years is not clear, but if there is, it's not very strong. And the reason we know that is that if you look back over long historical records and you count up the number of times you see a triple La Nina, they have occurred before, then it's once every few decades, and one might expect something like that purely by the coincidental occurrence in consecutive years, given the frequency of La Nina is every few years, if you see what I'm getting at. So it could just be coincidence that you get 3 on the trot. Sometimes we get 2 on the trot. Often you just get 1, of course. Looking at the frequency of those can tell you a bit about whether there's any real cause for that. In terms of the impacts, then there are very well-known impacts of La Nina starting in the Pacific. Then the tropical rainfall is displaced towards the maritime continent and Australasia. So you tend to get more flooding, for example, in northeast Australia, more flooding in the maritime continent, places like the Philippines and so on. And then, further east, there is a reduction in rainfall. So you can end up getting drought in places like South America, the west coast of South America. And then further afield, there's impacts on the monsoon. So we tend to get a strengthened monsoon during La Nina. There are impacts on places like South Africa, where we tend to get heavier rainfall in the austral summer season. So, yeah, I mean, we can trace these things out across the globe, basically. And East Africa is a particular region of interest at the moment because that often experiences drought during La Nina. And that's exactly what's going on at the moment. And the fact that we've had a triple La Nina has led to this multiple failure of the rainy seasons in East Africa and the very harsh conditions being experienced there at the moment. So again, these things sound esoteric and academic, but of course they have real world implications.
So very quickly then, Adam, would we say that what happened in Pakistan then, with all that very extensive flooding across the country during the summer, was that then linked as well?
I think that's right. La Nina enhances the rainfall over the South Asian subcontinent. We know that from computer experiments, forecasts, and observations. The center of action for that is often over India. It energizes the summer monsoon in India when we have La Nina. El Nino tends to do the opposite and increase the risk of drought. But of course, Pakistan is very close to India, and these things, being a fluid, they tend to wobble around a bit. And if you look at forecasts from ahead of the summer, then you could see that whole region had a positive rainfall anomaly. It was expected that there would be higher rainfall, and that can be attributed, at least to some degree, to La Nina. So I've no doubt that played a role.
It's interesting because we're talking about La Nina here and how it affected the monsoon in India, but I know that actually affected the jet stream one year and caused right the way around the globe really severe effects for the UK once it came back round again. And this is when we got Tewkesbury flooded and we just had storm after storm after storm. So it's interesting that something in the South Pacific can actually eventually influence the UK weather.
That's a good point. I mean, these teleconnections occur over a very long range. And so one might ask, how on earth does that happen? how can it be that, whether or not it rains more or less in the tropical Pacific could have an impact, say, on UK weather? And as you say, Jeff, there are now very clear demonstrations that that is the case. And that the way it works, I think we have at least a first order picture. We have a reasonable understanding of how that happens. It comes from something called a Rossby wave, which is a bit like a water wave on the ocean, or even in the bath, if you like. You disturb the water and you see a ripple spread. So the same thing happens in the atmosphere. If you disturb the atmosphere in the tropics, say by having a region of high convection and lots of rainfall, then that has a kind of knock-on effect, a ripple effect that propagates out of the tropics into the extratropics. And what you see when you do experiments like that in the computer models really is a rather amazingly simple picture. You see a sequence of high and low pressure regions spreading out from the tropics into the extratropics, and as you say, affecting the jet stream. The timescale, by the way, is about 10 days. So it takes about a week to 10 days. If you were to take a big spoon and stir the tropics now, then about 10 days later, you would see an effect halfway across the globe.
Taking you back to El Nino, Adam, curious about just how far back you can trace it. We believe that El Nino is responsible for the collapse of the Mayan civilization, and it may have assisted in the collapse of the Inca civilization by helping Francisco Pizarro to sail further down the Spanish coast, or sorry, the Peruvian coast. I just wonder if that's something where you look back through time, you can see these events coming up, not necessarily even in the data, but just in sort of in known historical events.
Yeah, I mean, there's a whole field of paleoclimate studies and using proxies, for example, to try and trace these things back through history. There are very interesting research papers on El Nino going back thousands of years using coral records, actually. So, as you know, coral bleaching occurs during El Nino when the tropical Pacific gets warm. The corals don't like that and they get bleached. And those records, you can find them in fossil corals going back thousands of years. And there's lots of debate, actually, about whether they illustrate the fact that El Nino has changed over those very long time scales. Of course, the problem is, as you go back and you look at proxies and things, and people do this for other parts of the world and these other patterns of variability using tree rings and so on, the uncertainties just start to, really increase as you go further back. So, yeah, people do what they can and extract what they can using very clever methods, but obviously the uncertainties inevitably increase the further back we go.
So, Adam, thinking about the future now, is climate change influencing or affecting any of our global oscillations?
That's another great question, Penny, and something that occupies researchers. Many hours of research have been done on this. Let's start with the simplest picture. The simplest picture is that climate change is warming the globe. We know that the globe is going to warm by a few degrees by the end of the century unless there's a massive reduction in greenhouse gas emissions. I think that's unarguable. The secondary question is what happens to the patterns of variability and these oscillations and things, because they are so important. As we've said, they make the difference between a drought year and a flood year in many parts of the world. So if they were to double or strengthen, my goodness, we could really see catastrophic changes potentially. I think first approximation, at least, then we can think of the globe warming and these oscillations just ride on the top of that, keeping roughly the same amplitude, but they ride on the top. So, for example, in Northern Europe, where we are, if you have a positive North Atlantic oscillation, you will no doubt have a mild, wet winter. If you add to that the climate change signal, then in those winters, we will get unprecedented wet and unprecedented warmth. But it's just because the oscillation has added to the mean change. It's like a wiggle riding on top of an ever-increasing curve. So that's the basic picture. And I think, from what we can see, that isn't too far from the truth. However, there are some cases where the impacts of these oscillations is changing. And one example is the El Nino that we were talking about. The El Nino and the La Ninas themselves, which we measure by the change in ocean temperature in the Pacific, don't show a very consistent change when we look out to 2100 in our climate projections. Some models suggest they change a bit, some models suggest they change the other way. It's a bit model sensitive. It's not clear that there will be a very strong shift in the El Nino or the La Nina itself. But what is clear is that the impacts on rainfall will get stronger. And so people have shown that the impact of El Nino on tropical rainfall will get significantly stronger in future. And that means that those year-to-year swings in the tropical regions that are affected by the El Nino and La Nina will also get stronger. And of course, that's worrying because it will add to the already difficult conditions that some of those tropical regions face.
I was just going to say, Adam, it's such a fascinating area of research and science to be in. And I imagine you're sort of learning new things all the time, which is fantastic and exciting. But I'm also wondering, as weather forecasters, one of the joys of our role is that we get instant feedback. So we forecast for tomorrow, and then we can see whether we were right or not the next day. You don't get that. Yeah, of course we are, Jeff. Yeah. But you don't get that in your role, Adam. So I'm just wondering, do you have to be quite patient? Is there any frustration? Are some of the shorter timescale oscillations like El Nino a little bit more satisfying in that context?
I mean, my first thought is it's all interesting, right, Helen? So
sure is,
that would be my first answer. And yeah, I mean, the impacts of these things in many cases justify the whole endeavour of investigating them because they are long-lived and they're prolonged. They are inevitably the things that are behind severe drought or prolonged flooding. It's always one of these oscillations behind it. So in that sense, you know, there's great interest and that's motivating. In terms of frustrations, though, I guess when we've made forecasts, sometimes it's very hard to, I mean, I think people do understand it, but it's actually very hard sometimes to get buy-in from people about the probabilistic nature of what we're doing. Because we're looking well beyond the weather forecast, even there we can't really be deterministic, as you well know, but because we're looking so far ahead, even in cases where there's lots of predictability like El Nino, it's always a probability. If we're looking 6 months ahead, we can tell you, okay, El Nino's favoured in the coming winter, you know, there might be a 70% chance, but that means there's still a 30% chance of the opposite. And that's not that the forecast is wrong. It's just, it does what it says on the tin, right? If it says 70%, then if I tell you that 10 times, then 7 times it'll happen, 3 times it won't. Just like forecasting the odds on anything. And sometimes getting that across to people is difficult because, of course, everybody wants a deterministic forecast. That would be even more useful. I understand that. But inevitably, we are limited by chaos in the atmosphere and the ocean. So we do as good as we can, but that can be a bit frustrating.
The whole subject is absolutely fascinating. I've written down so many questions here, but unfortunately we're coming to the end of the episode now. So I'd just like to say thank you so much, Professor Adam Scaife, for being our very special guest. Also, I'd like to thank our regulars, Helen, Catherine and Penny. I've been Jeff Norwood-Brown, and editors Clare, Nasir and Adrian Holloway.
Mostly Weather is a podcast by the UK Met Office. For the latest weather conditions where you are, download the Met Office Weather app.